Hello and welcome to the Semiconductor Industry Association's public webinar series where we discuss topics that are important to the semiconductor industry. My name is Robert Casanova. I am the Director of Industry Statistics and Economic Policy here at SIA, and I'll be your host and moderator for today's webinar titled How AI and Semiconductors Will Drive Innovation and Productivity in the Global Economy. Just a quick reminder, if you have any questions, please make sure to type your questions in the Q&A dialog box and not in the chat box. Before we get started, well, first let me introduce our panelists today. First, we have Jerry Chen. He's the Director of Global Business and Development for Manufacturing and Industrial at NVIDIA. Ramin Rohn is the Corporate Vice President of AI Product Management at AMD, and Stelios Diamantidis is the Distinguished Architect and Head of AI Strategy at Synopsys. We have a great panelist for today. Before I pass it along to Jerry Chen, I just wanted to share some data points just to provide additional context behind today's webinar. When we see, these platforms that are really driving innovation in AI, I'm talking ChatGPT, the use of AI in search engines, and data analysis, these platforms are really driving demand for AI semiconductors specifically. It's estimated that growth in revenue for AI semiconductors will be about 15% in 2023 and over 20% in 2024. So when we look at the potential for the semiconductor industry to become a $1 trillion industry by the end of the decade, AI is really going to be one of those major factors that really drive demand for semiconductors moving forward. By the end of the decade, really. So with that bit of information, I'd like to pass it along to Jerry Chen to begin the webinar.
Great. Thanks very much, Robert. And I'd like to thank the Semiconductor Industry Association for hosting this terrific panel discussion amongst these esteemed speakers. My intention here is, and my privilege is to sort of kick this off and kind of frame it in the sort of the general context of what NVIDIA has been seeing in the industry. And of course, as NVIDIA is obviously a semiconductor company ourselves, and we work with many of our semiconductor partners, including both panelists and their organizations. There's a couple of things that I think I'd like to highlight at the broad level, and then I think the subsequent speakers have a lot of additional technical details that I'm looking forward to seeing myself. So let me share my slides here. Can everyone see the slides okay? Okay. So first of all, we ourselves, of course, as NVIDIA, we're obviously a technology provider and an innovator in AI. One thing I'd like to point out, though, is that everyone, I think, would typically think of us as a hardware company. That's sort of what an average person off the street may think about when they talk about NVIDIA, or even in some cases, some of our investors. But I like to think back to a famous computer scientist named Alan Kay, who once said, "People who are serious about software build hardware." And we actually reflect that philosophy as a full stack technology company. People are often surprised to learn that we actually have quite a bit more software engineers at NVIDIA than we do hardware engineers. And it's because the hardware is sort of an implication and an outcome of our focus in specific industry domains and specific application areas. And interestingly, that's actually translated into the way that we're structured and the way we're organized. And it's actually translated quite well into our investments into accelerated computing as well as in AI. Now, of course, as a semiconductor company, as I mentioned, we're both a consumer of the technologies for accelerated computing and AI, as well as a technology provider to the industry. And that's sort of been very true. And a lot of the internal imperatives that we have, as well as our external customer-facing imperatives, are driving towards that goal, as being delivering technology solutions that are best in class from an end-to-end perspective. And it's much more than about the speeds and the feeds, and much more than about sort of the latest technology widgets. In the end, for us, as well as for our customers, you can kind of boil it down to essentially time to money. It's time to money, it's throughput of your workloads, and of course, it's the utilization of your infrastructure that you're using for this. Our CEO has systemically been pointing out that there's a new way that industries are starting to think about their own internal processes. And in the end, and they'll continue to have domain experts in different areas for excellence in their company. But increasingly, they're also thinking about how they can essentially create their own internal factories, not for hardware and for equipment only, but also factories to produce their own AI. All of these companies, NVIDIA included, and all of the companies that are on the panel here, have a history of lots of their own data that they've been generating over the lifetimes of their companies. That data can be harvested because it has a lot of latent value that can be used to improve their internal processes. So time to money in the end is absolutely true. This is true for fabless companies like ourselves. It's true for our foundry partners, and it's certainly true for the IDMs as well. In this picture here, I actually wanted to point out a couple of things that has occurred to myself and others that are looking at this industry at NVIDIA. So of course, there's been historically a focus on best-in-class tools as part of our own internal tool chains. And this will, of course, continue to be the case. We always need to get better results and better throughput for all of the jobs and job submissions and the workloads that matter to NVIDIA. But I would say that this is no surprise. I think many of the folks on the panel and in the audience have probably experienced this. This is actually increasingly also focused beyond just best-in-class tools to increasing or moving with the industry along a journey that's more about co-optimizing from end to end. And I truly mean end to end. So everything from the original algorithm design to RTL, to creating the net lists, physical design, and then finally the manufacturing and test. This is something that I feel like is a lot of sort of latent value that can be captured not just by internal processes and best practices from the human operations, but can also be augmented by AI co-pilots. And certainly, I think our friends at Synopsys and others know this extremely well, have been on this journey with us. And then we, of course, have our own internal tools that we're working on that are trying to do this and integrate them into tool chains from Synopsys and others. So, of course, in terms of improving the best-in-class tools, we will, of course, continue to still focus on the sort of straightforward acceleration of all these best-in-class tools. For example, we have spoken, and Synopsys has been kind enough to present some of these results at SNUG, as well as at our own GPU Technology Conference, GTC, some of the acceleration results with things like circuit simulation with PrimeSim. And of course, we've recently announced this terrific partnership around computational lithography using our cuLitho SDK in partnership with Synopsys, ASML, and TSMC. So this work will, of course, continue. It's got a lot of legs still. We're really just at the beginning of that journey. However, going forward, I think my sense, and I think a lot of the sense of folks in the industry, is that there is a lot of this latent value for injecting intelligence and automation into this end-to-end co-optimization journey. And we see this already starting to pay off with some of our own internal tools and some of the activities that we see at our partners and our customers, and we believe this is an inevitable trend. So let me speak a little bit about sort of what I mean by that. And I've already mentioned kind of this concept of this sort of duality of approaches that are converging together to help accelerate these workflows. And for this, I'm primarily speaking of ourselves and our downstream manufacturing partners. So as I mentioned earlier, so accelerated computing is a journey that we've been on now for approximately 20 years, longer if you consider some very domain-specific accelerated computing, like in graphics. This has really been a journey we've been on since the genesis of NVIDIA. And then, of course, more recently, over the last 10, 15 years or so, we've been on this journey with artificial intelligence. As everyone I'm sure is aware, the most recent kind of explosion in interest is around this concept of generative AI. If I could take a brief moment to kind of frame that in the way I think about it. So the earlier versions of AI and deep learning, they continue to be extremely powerful and surprisingly useful. But the way I kind of think about it is that there are essentially ways for harvesting data in order to make predictions. So things like classification, for example, or maybe even some type of forecasting solutions. These are a combination, in many cases, of more modern algorithms like deep learning and those related algorithms, as well as many of the traditional machine learning algorithm capabilities. But I should point out, and I think the industry is recognizing that generative AI is actually different. It's the genesis of all of these foundational technologies that we've been building on. But generative AI is the ability to essentially produce new data that is not part of the data set, or is not even it's not sort of a prediction about what it is most similar to in the data set. It's actually generating new content. And I think a lot of the things that we're seeing today, we're still just in the beginning. Many of these tools are fantastic and surprising, ChatGPT among them and others. But this is a journey that we're just beginning to take. And I think there's a lot of things that we can do to improve the capabilities for these generative AI tools, as well as to improve the domain specificity of that. But if you just look at the adoption, and again, ChatGPT, I think is a harbinger of this technology, but it in itself is still relatively nascent. But just the adoption of it is sort of an indication of how much people see some sort of value in it. I mean, I think a lot of the value that people see today, again, it's sort of in the sense of a fantastic toy, but that isn't to understate the value of it and how useful it could be for actual industry applications. And this is probably a well-known chart that many of you have seen before. If you kind of look at many of the most popular technologies out there, technology platforms out there, some of these biggest ones that have been wildly successful, if I take Facebook, for example, the number of months it took to reach 100 million users was 42 months. And that was that's a fantastic result. ChatGPT achieved 100 million users in 2 months from release. And that, to me, that's astonishing. And as many of you, I'm sure, have seen, there's some astonishing things that ChatGPT can do. But again, it's only the beginning. One of the things that I think is the most indicative, I think, of how useful it can be is the fact that it can be so multimodal. So it can be trained, not just, I mean, the ChatGPT example, most people are familiar with, is sort of text-based. So it's sort of trained on a corpus of text-based documents and data. There is a prompt. You're essentially requesting it to generate some content that's also in general and output in text format. And even that on its own is still fantastic and remarkable. But there are also other technologies that NVIDIA and others have obviously been investing in that are much more multimodal. So the prompt could be text, but the output could be video. The prompt could be images. The output could be animation. The prompt could be 2D input, and the output could be 3D output. The prompt could even be a description of what you're looking for, or characteristics and attributes that you're looking for. The output could be molecules or protein designs. So this is essentially why this technology is looking like it is going to be the next major trend, and we believe it's going to be driving not just solutions in our space in the semiconductor industry, but across all industries. In fact, we have already started to see this happen. This is no surprise. We have seen remarkable industry adoption and interest in investing in their own resources and their own time, as well as infrastructure and other things, in creating generative AI solutions that are domain specific and useful for them in their specific industries. And I love this chart because if I go back 22 years, the beginning of my time at NVIDIA, how broad and useful this is for some industries that maybe people wouldn't expect would be, the most technology forward types of companies. So sure, in semiconductor or in the internet and technology companies, nobody is surprised that they're adopting these these sort of leading edge technologies like generative AI, but food and beverages or in luxury goods and in consumer products and in retail, even in things like agriculture, we're seeing some of the oldest industries in human innovation starting to adopt generative AI technologies because they feel that it's useful. And I totally agree with that. And so just to wrap it all up, in terms of broader trends that we see in the computing era in our lifetime, so the first major driver, of course, that all of us have benefited from in our careers has, of course, been the PC computing industry. The internet sort of supercharged that and brought that capability and brought those technologies to a much broader space. And putting that technology in your pockets, of course, that's continues to be a driver. But this most recent trend that we're experiencing, and we're again just in the beginning of the hockey stick of adoption and innovation on, is of course in AI. And generative AI is the one that is the most obvious, the most compelling, and truly the most exciting that we see and expect to be a powerful driver for our own internal processes, as well as the customers and the partners that we work with. So I will pause there, wrap it up, and I'll hand it back to Robert.
Thanks, Jerry. Very interesting presentation. It's interesting to know that we're still in the beginning phases of AI, despite all the innovation and what we've seen so far. I'd like to pass it along to Ramin now from AMD to provide his insight.
Thank you, Robert. Thank you, Jerry. Okay, can you see my screen fine? Okay. So I'm going to talk about the challenges first for semiconductors to drive AI, to drive innovation and productivity. And I'm going to talk about how we address them. But before we start, I just wanted to say the term AI is very, very vast, very wide. AI could be referring to the chess program you were using in the 1980s to play chess with a computer, right? When we refer to AI today, it's probably deep learning. So machine learning was a way to do very shallow neural network, like classification type of stuff. That also happened in the 80s and 90s. And when we refer to AI today, it's really deep learning. It's the CNNs and the transformers and the generative AI of our time. So with that said, these are the challenges I see in continuing the exponential acceleration of the workloads that are being thrown at us in AI. One is, how do we scale after Moore? Moore's law being dead, but AI compute and the data to be treated, the big data that needs to be treated, continues to grow exponentially. And I believe our colleague from Synopsys will talk about that in length as well. But at the semiconductor level, we also need to address that. How do we grow it, improve exponentially when Moore's law is dead? And then how do we scale from very small to very big? Because we have AI in cell phones, in watches, and we have big iron cloud AI in the data center. One is optimized for a few milliwatts of energy consumption while still accelerating a lot of math. And the other one is optimized for extreme performance and kilowatts of power consumption. Obviously, you cannot take the same architecture and simply scale it up and down. The optimization points are different. The third challenge is obviously about sustainability. I mean, we do have one planet and we do have a finite amount of energy. So if we increase the compute capability exponentially, we have to do that at pretty much constant energy, which means really we need to bring down the energy consumption exponentially as well. And finally, the last challenge, and definitely not the least, is the matters of whether the output of your AI is safe, it's fair and unbiased, and it's legally compliant. For example, if you're using Copilot today to generate code, well, how do you know that the training data was licensed permissively? So you don't get sued for using that code, right? So a lot of companies are worried about that, and that's another challenge we need to address. And I'm going to go and pretty much one by one and show how we're addressing these. So first, in terms of scaling the architecture up and down from very small to very big, and also post-more, we have different architectures that address different problems. For example, for big iron cloud GPU training and inference, we have the CDNA architecture, which is a compute GPU architecture. Whereas for the smaller edge and tiny endpoint AI accelerators, we have the XDNA architecture, and X really came from the Xilinx acquisition, which are very strong in small SoCs for embedded applications. I will show some example. Obviously, there is the Zen architecture for CPUs. Believe it or not, most inference workloads are still run on CPUs, and they have things like vector math, vector accelerators to run those. And finally, for laptops, there is a Ryzen AI mobile processor that we have released, and it's in laptops, in stores already, only a year after the Xilinx acquisition. It includes Zen, XDNA, and the RDNA, which is the graphic GPU architecture. So we have all this different architecture, and we can put them together or not to address the very small and the very big. And that also helps us in the post-Moore era, because since the improvement, the exponential improvement, is not coming from silicon scaling alone, it has to come with architecture innovation. And those different architecture are evolving every couple of years, every generation, to bring a 10x or whatever x is needed to have the 2x improvement every couple of years. And obviously, software is very important. And our philosophy for software is really that it has to be free and open. And that will fix basically the safety, the bias, and the compliance issue. It has to be free and open, and we're partnering with like-minded ecosystem partners who provide free and open data that are permissively licensed, so you can use to train a model, or use their model, which is also permissively licensed. Hugging Face, for example, has a code generation large language model, which is completely permissively licensed, and with data that they provide also, which is free, open, and permissively licensed, that are GitHub, obviously, code, but only the ones that are Apache or MIT permissive licenses. And then on top of that, user experience is extremely important. If you're providing AI from endpoint to cloud, you want a seamless user experience. So we're working on a unified AI front end to have one user experience for the XDNA, the CDNA, the RDNA, and the Zen architectures. And those are some of the markets that we're addressing today. We're shipping AI accelerators to today. And we don't ship them only on Earth. We actually have chips of ours on Mars in the rover today. We had a chip in the landing system, and we have a chip in the rover for the self-driving and all the visuals, the computer vision, and the AI that are run in those algorithms. Those are tiny little hardened Xilinx chip. You can imagine the amount of radiation those chips have received on the trip, and the conditions on Mars. So those are extremely hardened aerospace chips that are computer vision and AI capable. We also have chips on satellites. Thousands of satellites today have AMD chips on them, and same thing, they do computer vision. There might be some AI, like detecting whether a white patch is a cloud or it's actually something on the ground. And we have chips that landed on comets to extract pieces of it and bring them back to Earth for analysis. And then maybe closer to Earth, but still related to aerospace, we also have chips at the CERN doing sensor fusion and extremely rapid analysis after proton collisions in the accelerators. And we were actually part of the pipeline that discovered the Higgs boson there as well, because they need chips that can get a lot of data and analyze them extremely quickly, because after the collision of two protons, the millions of particles that are created vanish extremely quickly, and you have a lot of those collisions per second. So you have to be able to compute things very rapidly on the fly. Automotive, obviously, there is AI everywhere in the automotive. Actually, that's one of the deep dive slides I have next. So I'm going to skip it for now and show you that in the next slide. In healthcare, AI in healthcare, I would say, really exploded during COVID. We had a lot of companies using our chips to analyze X-rays of lungs to see if the lung issue is COVID related or not. X-rays, analyzing CT scans, CAT scans, PET scans for things like cancer detection also. And we have, obviously, in medical research, companies using AI for cancer treatment research, for example, as well. Illumina is using our chips also for genome analytics, and they happen to save babies in children's hospital by analyzing the genomes of babies who are sick, so they can quickly determine the possible root causes and treat them. And with AI accelerators and compute accelerators in general, they can do that within minutes versus days before. So literally saving babies' life in children's hospital. In industrial, obviously, robotics with AI, robotics combined with AI is a huge productivity boosters on production lines, and not just building products, but moving packages in Amazon warehouses or Walmart, and also to look at the quality of the objects that are going through the production line. So defect detection and so on. In communications, again, with the Xilinx technology, we're pretty big in wired and wireless communications. 5G and Ethernet are going through AMD devices, AMD accelerators, XDNA. Every bit of voice that you're hearing right now is going through an AMD device, whether it went through a cell radio through 5G or wired infrastructure. And AI is becoming more and more pervasive for wireless as well as for wire. For wireless, it's for improving traffic management, for example, and for wired, it's more about threat detection and attacks, attack prevention, and so on. For smart PCs, I talked about Ryzen AI. So that's a laptop that's AI capable. What does it mean? It means we have a little AI accelerator that accelerates the AI that's behind me, the virtual background, the background blur, the eye gaze correction that may come in the next Windows, in the next Teams or Zoom, and so on. And I can tell you that what I see is that in a very near future, I'm not talking years, I'm talking month, there will be OS that will be AI capable. And what does that mean is it will be able to analyze what you're working on, of course, if you allow it, your documents, your visuals, your PowerPoint, your Excels, your code, and on your prompt, it can finish your job. It will be able to finish your docs, your presentation, your macros, your Excel macros, or your code. And it will be always aware of everything you're doing, and it will remember better than you what you did a year ago, a week ago, a month ago. With vector databases, that's the memory of AI and generative AI. It will be able to remember everything you did in the past several years, and on your prompt, it can use all that knowledge to finish your work. So that's a massive, massive, massive productivity boost, which I don't think we can totally fathom right now. But I think you and I will be probably 2x, 10x more productive in the months and years to come. And then obviously AMD is very strong in data center, whether it's CPU or GPUs and in supercomputers. I put some of the supercomputers that have our GPUs here in the number one of the top 500 supercomputer list in the world is Frontier, that has AMD CPUs and GPUs. Lumi is the number one in Europe, number 3 worldwide, which is also AMD CPUs and GPUs. And even hyperscalers are in the top 500 of supercomputers now. Microsoft Azure has the number 11, which is also AMD CPUs and GPUs. And obviously, all the scientific computing, the weather forecast, the medical research, large language model training and inference are done on those supercomputers. Lumi, for example, built the first Finnish LLM, large language model, on that supercomputer. I promised you a slide on automotive. So what's amazing on automotive is that when we say AI is everywhere in the world and in all markets, it's also true in automotive. AI is everywhere. And we literally have all those chips in a single automotive. And that's from an infotainment, like Ryzen, the Ryzen APU, which has a CPU and a GPU, is in Tesla today, as you know, that was announced. So we go from infotainment, like Tesla, to ADAS, which is driver assistance, to AD, which is autonomous drive, to front camera, LiDAR, 4D radar, analysis, sensor fusion and analysis to understand the environment, to build a surround view for parking, and in-cabin monitoring. In-cabin monitoring is all about saving lives also. Like you may or may not want to deploy an airbag in case of an accident, depending on the passenger situation. For example, if you have a newborn that's facing the airbag, you may decide not to deploy it. Or if the driver is getting sleepy, you want to beep a little to wake him up. So all those things are using AI in one single vehicle, and it's AI everywhere in one product. So when I talk about edge and endpoints, the car is the edge, and those are all the endpoints. And finally, we need technology advancements to boost AI, to boost computational power, memory density, memory bandwidth density. Large language models are extremely memory bandwidth limited, like no AI before that was. And you need a lot of HBM memory, for example, and a lot of bandwidth. And the type of technology innovation AMD has been involved in, namely advanced packaging with chiplets, 2.5D integration, 3D integration, help this a lot. Because when you integrate things in 3D, sorry, like for example, the example on the right, that's a 2.5D integration. You have the IO and SRAM, the caches in the middle, and then you have the CPU dies on the side. You have 12 of them here. But then there is a little 3D here you don't see, is that little pinkish stuff on top of the CPU die, that's a 3D cache. So that's more memory and more memory bandwidth put on 3D, die on die. And on the left-hand side, you see the same level of 2.5D integration. You see the HBM on the side, the black dies. And then you see the big dies in the middle are GPU dies, and the small dies with the little pinkish thing in the middle, those are CPU dies. So that's really an APU. It has GPU and CPU. But what you don't see is that underneath that, there is the IO die. As you can notice, you don't see the middle IO die that you see on the right. That's because it's underneath. And the caches, the SRAMs are also underneath. And you can never pack that much memory bandwidth, and that much compute in just a 2D die. It won't happen. So that's die on die, extreme integration that allows for extreme compute power and extreme memory and memory bandwidth. And that takes me to my conclusion slide. So how do we fix those challenges? More than more is really fixed by domain-specific architecture. All those architecture I talked to you about, the Zen, RDNA, CDNA, XDNA, they're basically domain-specific architecture that we're fine-tuning more and more for AI, whether it's training on one side, inference on the other. How do we scale from very small to very big? We provide all those devices. Well, that's with fine-tuning the DSAs, creating variation, and also creating different optimization points. You want to optimize for low power for an endpoint. You want to optimize for high performance for data center. And obviously, performance per watt will always be good, but the optimization points are different. Sustainability. How do we ensure that we're not going to use more than the power we need? Well, that's basically done with the advanced packaging, chiplets, 3D integration that I talked about. The more you integrate things, the more the communication is going to be low power, and communication is where most of the energy is consumed. When you go out of your device to go talk to external memory, most of the energy is consumed there. The more you integrate, the more sustainable you're going to be. On top of having DSS and all that obviously very good for power efficiency as well. And then in terms of safety, fairness, and compliance, as I said, we fix that with an open ecosystem, open source community, permissively licensed data and models, and so on. Okay, giving it back to you.
Ramin, thank you very much. That's a great presentation, a lot of great information. I don't know how I feel about the smart PCs and AI and the operating systems right now, but we'll see in the future.
We'll see that in a year.
Yeah. So I'd like to pass it along to Stelios now to present on behalf of Synopsys.
Wonderful. Robert, thank you very much. Jerry and Ramin, you made it very hard for me. I'll try to live up to your standards as much as I can, but I really enjoyed the content so far. So from Synopsys' point of view, I thought we'd take a bit of a look as to how we can enable these innovations from the point of view of really atoms all the way to software. This is really what customers are looking for and what technology evolution is looking for. And I think looking at the both your presentations, I really walked away with this constantly evolving picture of technology and economics meeting each other, and it's something that it's an option we call techonomics. And I think very clearly from your presentations, I think we live in an era where smart everything is driving the economic agenda, whether it is at the data center, in industrial environments, in healthcare, in our hands, day in, day out, in our smartphones and our wearables, and certainly in automotive more and more. And this, I like this chart because it sort of captures the fact that the sort of data generation environment was handed off from humans to machines quite some time ago. So now we're just following an exponential growth in data availability and data generation itself. And this is prior to generative AI. It came from high automation environments. So data is growing, and it's growing at an exponential pace. no surprise that technologies are also growing and are trying to match the rate of growth of data to enable smart everything. So we've seen exponential model size explosion, for example, in the last few years. And this is prior to the more recent large language model revolution. So you can see, the compute requirement to train models that have been around now for some years well outpaces Moore's law and has been for some time. Then in more recent years, with incredible innovations in large models, transformers, we have taken that pace from what was about 8x every 2 years. Now it is close to 300x every 2 years, and doesn't look at abating that pace of compute requirements. So pushing the limits of compute. And then, of course, that means more and more and more chips, which is great news, of course, for the semiconductor industry and for all of us. More and more chips that are able to consume this data, bring it in to the compute environment, deliver the computations, and do so with real-time constraints and with tremendous energy constraints. And talk about energy, that is not looking too great either, right? The more compute evolves, the more we start measuring, not in terms of milliwatts, like a lot of us were used to some years ago, but more in terms of yearly home energy budgets, which in fact has led to a tremendous innovation in its own right. The ability to deliver performance per watt has truly skyrocketed, but so has the incoming compute load. So we certainly see that the energy requirements are also growing exponentially, and maybe that leads us to the most important exponential of them all, which is our environment and our climate. So the economic pool is strong right now, primarily driven by AI applications in all these different vertical markets and segments. So whenever you have a taxonomic pool for new capabilities, you need a taxonomic push to give you the engine to deliver those capabilities. So let's take a look at that. What's going on with that taxonomic push engine? And in semiconductors, of course, that's something that we've been calling Moore's law for a long time. And we can see that from a computer, so from a compute density, if you like, transistor density perspective, that taxonomic engine has been slowing down for some time. Now, interestingly enough, we continue to push into what currently is the angstrom era of devices, and folks have been announcing the death of scaling evolution for some time now, but smart engineers keep outsmarting the Cassandras here and coming up with new capabilities and new ways to beat the curve and create smaller devices and scale them. But certainly the rate and certainly the cost have been on a different curve for some time now. Now, other technologies have come in to allow us to do things to continue the evolution of Moore's law, but maybe in another dimension. And I think Ramin mentioned that a little earlier, 3D integration, whether it's 2D or as we go forward into true 3D, a vertical integration where you can have multiple dies stacked on top of each other, communicating and optimized for certain workloads, have been enabled by our ability to deliver the interconnects, the micro bumps, if you like, at astounding density. And not only astounding density, but also astounding energy requirements. And that has really led us into an era that we like to call the SysMoore era, or the systemic Moore era. Now, the devices keep growing, single die monolithic devices keep growing, but the integration of these devices allows us to drive the complexity into another axis called systemic complexity. And this allows us to innovate architecturally at a rate that we have never done before. And this can be the integration of memory compute, the integration of sensors into the stack, the growing ability to transfer data in and out of the systems, and of course, the chiplet-based design paradigm that is now taking hold and is driving really, really hard. So from Synopsys' perspective, this is all great, and we see this as a vehicle and as a capability that will allow the industry to move forward. But systemic complexity has a profound effect also on our ability to innovate at the rates that we need to innovate to enable it. So if we look at EDA, this has been the story of our industry for quite some time. In the 1970s, circuit simulation and layout and digital simulation were essentially instrumental in creating some of the very early integrated circuits. And those were well into the computer-aided design era, where an engineer would actually interact with a machine and draw things out very manually. Then a major revolution happened in the, let's say, mid-1980s or so, where we were able to design circuits programmatically with the invention of synthesis and then automated place and route. So that gave the industry a huge boost. And then at that point, I think, and that also heralds, of course, the creation of Synopsys as a company itself, maybe we have the transition from computer-aided design to electronic design automation being the operative word. And from that point on, other major innovations have been able to push productivity forward. Perhaps a major one was the ability to package and reuse designs at significant scale with intellectual property components. Then as manufacturing challenges became more and more integrated, then the integration of engines and capabilities into a sort of a hyper-converged infrastructure led to the fusion together of different tools into entire platforms that can perform optimizations, not only in a clock domain or in a routing domain, but literally from, say, an RTL description all the way to finally optimized fully interconnected topologies. And what we're observing now, and has and by the way, this growth and this continuous step up in productivity ran to the tune of about 10 to the 7x productivity for designers over this 3 or 4 decades, right? So really stepping up to that challenge. But as challenges become more systemic and architecture becomes dominant, what are the future waves that will allow us to deliver the next 10 to the 7x designer productivity? And really, this is where AI is coming into play. And it happened organically, quite honestly. It didn't happen through a grand master plan. It happened through the continuous innovation and integration of technologies well within existing tools and methodologies, some of them small, some of them bigger, the ability to predict downstream effects more effectively by collecting data on prior, for example, design evolutions, the ability to classify design effects so that you can tackle them more efficiently in different environments, the ability to learn post-deployment, meaning while engineers are actually running tools, and tune the engine so that they can perform more efficiently. All these capabilities organically entered the design stream and started offering really nice productivity boosts. But we feel the major step forward came forth a few years ago with the introduction of design space optimization. And design space optimization is a capability that was introduced in 2020 and leveraged a huge body of knowledge in reinforcement learning technology that I think first became quite popular and visible with the introduction of machines that could learn how to play complex games of strategy like Go or chess. A great example being DeepMind's AlphaGo, AlphaZero, MuZero technologies. Now, these capabilities allowed us to ask questions of if we can design circuits and if we can organize circuits into IP and incorporate them into complex designs, can we actually hand over to machines more important aspects of design, which is, for example, searching spaces that our current tools simply were not able to search due to scalability and capacity limitations. So design space optimization came to essentially extend the concept of design space exploration, which is very well understood across many design domains, not only design automation or semiconductors. And it's the concept of being able to search your design space and formulate hypotheses that then you go out and pursue with what-if scenarios and validate with metrics. If, for example, you conceive of a design space as a 3D surface where you're trying to co-optimize competing objectives, most usually your energy consumed, so power, the area of the circuit, which has a directly reflects of the cost of the device, and of course, how fast you can actually perform the computation. engineers would actually design experiments and then would use tools to explore the design space and find solutions. Now, the design spaces that they had to explore are vast because they include multiple dimensions of design. It's the place where you have architectural decisions that meet implementation decisions that meet manufacturing environments, libraries, constraints, technology files. So it's a very heterogeneous environment of separately optimized design silos. The bandwidth of exploration is generally quite slow as engineers have to consume a lot of data, have to make decisions under very stressful conditions, and then typically find a promising area of the design space and tend to hone in that design space for some time. With design space optimization, which is this paradigm, and we put a lot of these decisions directly into the control of AI reinforcement learning agents. And those reinforcement learning agents can autonomously explore the design space and decide what mix of exploration, i.e. completely new areas, versus exploitation, which is known good areas, would be required to perform certain explorations, optimizations. So this way, not only would they identify promising areas of design, but they would hone into those areas and spend more compute bandwidth in areas of promise versus areas that have been disproven as promising areas. So the augmentation of bandwidth in search and the augmentation of bandwidth in decision-making has led to significantly better power performance areas results. In practice, when you're looking at competing objectives, it would look like this. You would have a result that designers were able to achieve through lengthy experimentation. Then you would have a swarm of results that would actually pursue, and in most cases exceed, what the designers are able to do. In this case, co-optimize timing and power, so down and to the left, and then arrive at better results that can be directly used by the design teams. This leads to something we've started calling AI-grade productivity. So if you're looking at any design team's missions, you have the three competing objectives of the quality of results you're trying to achieve, the time to results, so that's your schedule, and then cost of results, and that's really your investment in compute as well as your engineering effort to get there. So with this AI level productivity, we would see actually improvements in all three axes concurrently. So you would get significantly better power in less time, sometimes several times faster than traditional design convergence, and in many cases by a single engineer versus a team of experts. This is, again, by virtue of the augmentation of the exploration bandwidth, but also the ability to learn and apply the prior learnings, not only on a designer by designer basis, but also at the level of an entire team working together. Particularly important in an industry like ours, where experience doesn't come a week or a month at a time, but mostly a decade or two at a time. So now that we have this capability, reinforcement learning and design environment, what do we do with it? So this is our journey at Synopsys. We introduced design space optimization in a product called DSO-AI acronym back in 2020. That same year, we were very honored to receive a great distinction by EE Times as the year's most innovative product for design. In the next year, as more and more customers started using the technology, we started seeing sort of records of productivity being broken. Great example, one of our customers who came and talked about being able to perform a full implementation from RTL to final GDS for 10 blocks with a single engineer. This is an environment where typically you would take 1 to 2 engineers per block. So a good almost 20% increase in productivity, in measurable productivity for a production quality design. And then I think a seminal point was a few months later in 2021, where we actually heralded likely the world's first AI design chip in the industry, based, of course, on our accounting. But it was not really one. It was really a swarm of capabilities as we started working with semiconductor leaders like the folks here on the panel today to deploy this technology, which today has been accepted by almost all the top 10 companies in the world and has led to over 200 commercial tape outs using this technology. But it was truly exciting, I think, for the industry is the fact that this reinforcement learning driven paradigm didn't stop there. In fact, it was the beginning. This year, we announced a new suite of AI agents that can operate not just physical design, but really the entire design stack, from intent-driven verification to digital implementation to test and to manufacturing. In verification, for example, and this is a presentation or a result presented at a recent SNUG event, may or may not have been by a company that's represented here today at the panel. You can see how reaching 100% coverage, which is the objective of teams, takes time and takes a lot of tests, a lot of compute. Typically, those tests are random, constrained invocations of different classes of tests, and they can take, in this case, actually, over 1,000 passes to reach the target. With AI technology, we can wrap around the design environment and we can direct those generators so much more efficiently than pseudo-random. You can see how a verification space optimization technique reaches 100% significantly faster than the traditional technique. In this case, reach 100% when the traditional constrained random approach has barely reached about 1/3 of required coverage. So it's tremendous productivity benefits. And then proceeds to extend coverage through smart engines that now have time to say, well, you've missed some things. Let me go and pursue my own coverage and show you that I can actually find more bugs in spaces that the designer did not anticipate early on. Another area that's very important for our ability to scale into the next generation of domain-specific architectures is our ability to test these devices. And I think Ramin touched upon this, and so did Jerry early on. Test is a huge bottleneck, and as the technologies have evolved, the fault models have evolved, the design has become more complex, but markets have put tremendous requirements on good parts on all our customers. We have seen the pattern counts for semiconductor devices actually skyrocket by 3 orders of magnitude or more over the past couple of decades. Now that directly translates into cost of goods sold expenses here, which are extremely important if we are going to make technology available at costs and accelerate its proliferation. So with AI, we can more efficiently search the test space, and even for given architectures, without actually changing the way that the functionality is performed or the way that the test infrastructure is designed, we can compress the vector sets to the tune of, in many cases, 20% or more, in this case, 43%, and this is production quality design, which directly translates into significant cost savings as every improvement is multiplied by the number of parts manufactured. So to summarize, we have seen really a growth and a huge potential in the use of AI technologies in designing semiconductors, from modeling new materials all the way to constructing very large chiplet-based systems. First wave came in having surrogate models that were inserted in tools to improve their predictability and performance. I think a major step forward was realized with the introduction of systems that can search design spaces across really the entire stack of data abstractions in semiconductor design, and really optimize our outcomes and help us improve our decisions. No doubt in my mind that the next step in evolution will come through the introduction of smart assistants that will leverage this new wave of large language models and generative AI to help us explain outcomes better. And by explaining, I mean, give us the ability and to give engineers recommendations as to what to do next, how to drive their exploration, how to design their code, how to apply better standards and styles, how to automate debug, and then even interact with the design environment through natural language. But really the destination is something that I think would be a sort of a holy grail here, and that would be the ability to truly create generative design, going back to Jerry's diagram of multimodal generative AI systems that can consume the many different aspects of a heterogeneous system and translate those into the many different data that is required to create integrated circuits and systems. to prescribe outcomes and allow folks to outsource entire tasks to AI agents. And with that, I really appreciate you having me on the panel.
Stelios, another great presentation. Thank you so much. That was a lot of very interesting information on how AI is really driving the ability to increase innovation in semiconductors. We're at the top of the hour now. I'd like to at least take the time to thank my panelists, Jerry and Ramin and Stelios, for really showing how AI is going to not only continue to innovate in semiconductors, but also the downstream effect of how it's going to really allow those other end market industries to take advantage of what AI has to offer, and especially the hardware that's going to be needed to drive this innovation. Just for everyone's information, the webinar has been recorded and will be on the website, as well as the presentations on the SIA website tomorrow by noon, and so you can have access to that. Again, I'd like to thank my great panelists, and we'll end the webinar there. Thank you.
Thank you very much.